Well, hello everyone, and welcome to our calculus notes for section 4.4a, the fundamental theorem of calculus. So informally, the fundamental theorem of calculus states that differentiation and definite integration are inverse operations. And integration, therefore, undoes differentiation. We now have a way to evaluate definite integrals without using the limit definition. So here is the fundamental theorem of calculus. It says if a function f is continuous on the closed interval from a to b, and capital F is an antiderivative of f on the interval a to b, then we know that the definite integral from a to b of our function f at x with respect to x equals the antiderivative capital F at x evaluated from a to b. And what that means is we need to find the antiderivative evaluated at the end point of our interval and then subtract the antiderivative evaluated at the beginning of our interval. Super, super simple and pretty amazing. So let's go ahead and work on evaluating each definite integral. So what we want to do is focus on our x squared minus 3. And what we need to do is come up with the antiderivative of x squared minus 3. So we are going to use the power rule here. And so we get x to the third over 3. So we raise the power 1 and then divide by that new power. And minus 3 turns into minus 3x. Now in this case, it's important to note, since you are subtracting these from each other, if you had a plus c here and a plus c here, those would essentially cancel each other out. And so you don't need to worry about that when you are taking your definite integrals antiderivatives here. Now we're going to evaluate this from, we're going to use this notation, 1 to 2. So 1 being the starting position, 2 being the ending position. And so what that's going to mean is we're going to find capital F at 2 minus capital F at 1. And so capital F at 2 will basically just take 2 and plug it into the antiderivative. So 2 cubed over 3 minus 3 times 2. Okay, and there's capital F at 2. And then minus capital F at 1. So that's going to be 1 cubed over 3 minus 3 times 1. All right, now we just need to calculate this here. So we have 8/3 minus 6, and then minus 1/3 minus 3. All right, 6 we could think of as 18/3, so we have negative 10/3 here. And then 1/3 minus 3, 3 we can think of as 9/3, so 1 minus 9 is negative 8/3. We'll distribute the negative and be left with negative 10/3 plus 8/3 is negative 2/3. So that's how to use the fundamental theorem of calculus to calculate these definite integrals. So we're going to do a couple more examples here. We're going to do one with a radical, and then we're going to also do something where we have x in the denominator. All right, and so here, before you find this antiderivative, we do need to rewrite this. So this will be the definite integral from 1 to 4 of 3x to the 1/2 power with respect to x. All right, so now when we go ahead and find that antiderivative, we'll have the constant multiple 3. We'll raise the power by 1, which is 3/2, and we'll divide by 3/2. Now this we want to get evaluated from 1 to 4. Now before we do this, we might want to clean this up a bit and simplify. So instead of dividing by 3/2, we're going to multiply by 2/3. So it is 2/3 times 3x to the 3/2, evaluated from 1 to 4. And we can clean that up a little bit more. The 3's will cancel here. So we have 2x to the 3/2 power, evaluated from 1 to 4. Now we're going to do capital F at 4 minus capital F at 1. Fundamental theorem of calculus there. So if we plug 4 in, we're going to get 2 times 4 to the 3/2 power minus 2 times 1 to the 3/2 power. All right, so you can think of this as first off taking the square root and then raising that to the third power. So the square root of 4 is 2. Raise that to the third power, you get 8. 8 times 2, we have 16 here. In this next one, we have 1 to the 3 halves, and so that's going to equal 1. So we just have minus 2 here. And so all in all, we get 14. All right, let's try letter C. Here we want the definite integral from -3 to -1 of 1 divided by x squared with respect to x. So here, we do want to rewrite this in a power form. So this will be x to the -2 power with respect to x. All right, so we do want to find our antiderivative. And so we're going to raise the power by 1 up to -1 and then divide by that new power. And the definite integral says we're going to evaluate this from -3 all the way to -1. Now before we actually plug everything in, let's go ahead and simplify here. So this is going to become -1 over x from -3 to -1. Now we'll use the fundamental theorem. So we want the antiderivative at -1 minus the antiderivative at -3. So we'll plug those values in. We get -1 over -1, and then minus -1 over -3. So lots of negatives to consider here. Just have to keep them all straight. This becomes positive. This is positive. So we really have 1 minus 1/3, which will leave us with 2/3. All right, moving on to our next example. Now we have an absolute value. And so we're finding the definite integral from 0 to 2 of 2x minus 1. Now, when we think about this, absolute value is actually a piecewise function. And so we're actually going to have two different functions here, and they're going to split at 1/2. So when we think about the absolute value of 2x minus 1, this actually is a piecewise. Okay, and so this is going to equal 2x minus 1 whenever this is a positive value. And so this is going to be when x is greater than or equal to 1/2. Now, it's going to be the opposite of this every time it's a negative value. So it's the opposite of 2x minus 1 whenever we are less than 1/2. Okay, so we actually have two functions here on different intervals. And so what we can do is we can actually split this up, and we have the interval from 0 to 1/2, and that's going to be this negative portion. And so that's going to be the opposite of 2x minus 1 dx. And then we can add that to the second portion, which will be 1/2 to 2. And that's going to be of the 2x minus 1. All right, so in this case, we actually have two definite integrals to solve here. And so we'll just do the first one here. We probably should distribute that negative. And so that would become positive there. That'll be a little bit easier to look at. All right, so for the first one, the antiderivative will be -2x squared over 2, and then plus x. And we're going to evaluate that from 0 to 1/2. And for the second one, we will have 2x squared over 2 minus x, and we'll evaluate that from 1/2 to 2. All right, and we can simplify this down a little bit. We'll get rid of the 2 over 2. We'll get -x squared plus x from 0 to 1/2. And then we'll have x squared minus x from 1/2 to 2. All right, so we got to substitute the upper limit in and subtract substituting the lower limit in. So it's going to be negative of 1/2 squared plus 1/2. And then minus, we're going to substitute in 0. So -0 squared plus 0. And then we're going to do the second one. So we're going to plug in 2 and then 1/2. So it's going to be 2 squared minus 2. and then minus 1/2 squared minus 1/2. Okay, so lots of parentheses, lots of things to keep sorted out there. Let's go ahead and solve this. Here we're going to get negative 1/4 plus 1/2, and then this is 0. On the right-hand side, we're going to have 4 minus 2, and then minus, we'll have 1/4 minus 1/2. We'll clean up some of these fractions here. This turns into 1/4. We still have the plus. This is 2, and then minus. This actually is negative 1/4, which will become positive 1/4. So we have 1/4 plus 2 plus 1/4, and we get a grand total there of 2.5, or 5/2 in total. All right, so with those absolute values, you just got to split them up into the two different portions. Sometimes the graph is helpful, so you know where that is. Otherwise, you have to set the 2x minus 1 equal to 0 to find where it switches from positive to negative. And so you can see when you add the 1 and then divide by 2, you can tell that at x equals 1/2, we have a 0, and so that's where it will switch on that interval. All right, we're going to use Fundamental Theorem of Calculus one more time here, and we're going to want to find the area under the graph of y equals 2x squared minus 3x plus 2 from x equals 0 to x equals 2. Now, this is going to be possible as long as the function is non-negative or positive from the interval 0 all the way to 2. Now, in this case, it is, and so this area right here will equal the definite integral from 0 to 2 of 2x squared minus 3x plus 2 with respect to x. All right, so we know we can take the antiderivative, so we get 2x cubed over 3 minus 3x squared over 2 plus 2x, and we're going to evaluate that from 0 to 2. All right, so again, the process says we plug in our upper limit of integration, which is 2. Okay, and then we're going to subtract the lower limit of integration. So we're going to plug in 0 into our antiderivative. Okay, so here we have 2 cubed is 8, times 2 is 16, so we have 16/3. Here we have 2 squared, which is 4, divided by 2 is 2, so 3 times 2 is 6, and then plus 4. And then all of this over here, when you plug in 0, you actually get 0, so that'll be minus 0. All right, negative 6 plus 4 looks like negative 2, and negative 2 is equal to negative 6/3, so 16/3 minus 6/3. And so overall, we get 10/3 for that area. All right, so that is the fundamental theorem of calculus and how we can use it to find definite integrals.